Hello, my name is Anssi Kanervisto and I'm here to tell you about our work on an initial investigation on optimizing tandem speaker verification and countermeasure systems using reinforcement learning. So that we are all just on the same page, speaker verification system verifies that the claimed identity and the provided speech sample are the same, come from the same person. So automatic speaker verification system takes in a claimed identity and some speech sample, and if the identity matches the identity of the who spoke, then all good, the system will pass. And then likewise, if somebody else claims that they are someone who they are not and provides a speech sample, it shouldn't let them pass. All good, very simple, many of you work on this field. Of course, when it comes to security and systems like this, there are some bad guys who want to break the system. So, for example, in this case, somebody could record Tommy's speech here with a mobile phone and then later use that recorded speech to claim that they are Tommy by saying that they are Tommy and playing the audio, and the system will gladly accept that. And previous work has shown, the SPSproof 2017 challenge showed that if you don't protect for this, the ASV system will gladly accept this kind of a trial, even though it shouldn't. Likewise, you could use a gathered dataset or collect data of somebody speaking and then use speech synthesis or voice conversion to again generate speech that sounds like Tommy and feed it that to the system, and it will again accept it all fine. And again, this has been shown in previous competition. It's a problem, but you can also fix for this. So this is where the countermeasures come in. So a countermeasure system takes in the speech sample that was provided to the ASV system as well, and also checks that the sample comes from a human speaker instead of like a mobile phone, or it's not synthesized speech or voice conversed speech. So it's like a bona fide human speech. So for example, somebody has recorded somebody else's speech, feeds it to the system, but now it's fed to the countermeasure system as well, and the countermeasure system says it's a reject, and then the attacker does not get access, so it leaves a sad attacker. All good so far, and these competitions have shown that when you train for these kind of situations, you train to detect these replay attacks or these synthesized speech, you can detect them and all works fine. So, but one nag we had with this setup is that the ASV system and the countermeasure system are trained completely independent from each other. So the ASV system has its own dataset, its own laws, its own training protocols, and so on and so on. And likewise, the CM system has its own datasets, its own laws, its own training protocols, and its own network architectures, and so on and so on. But these are trained separately, but then they are evaluated together. So they are evaluated as one bigger system. So where you have a completely different evaluation metric, and these two systems have never been trained to minimize actually this evaluation metric. They have been trained on their own tasks. So we had this coffee room idea where what if when we have this kind of a bigger whole system, what if we train the ASV and the CM system on the evaluation metric directly? So maybe on top the already existing training they had, we also optimize them to minimize or maximize the evaluation metric for better results. However, sadly, it's not so very straightforward. So we have this system where we feed in speech to ASV and CM system. They produce, both of them produce like accept and reject labels, so either accept or reject, and these are then fed to the evaluation metric, which usually computes the error rate, so false reaction rate and false acceptance rate. And these are then used in various ways depending on the evaluation metric to kind of come up with a one number to show how good the system as a whole is. However, if we assume that these two ASV and CM systems, they are differentiable, so they are like neural networks, which is quite common these days. If we wanted to minimize the evaluation metric, we would need to compute the gradient of the evaluation metric with respect to the two systems we have or its parameters. Sadly, we cannot compute the gradient over this hard decision of like accept reject, but these are required for the error rates for the evaluation metrics. So for example, the tandem decision cost function, which we will be using later, requires these two error rates, and it's going to weight them in different ways. But we can't from that go back to the compute the gradient all the way back to the systems, because this hard decision is non-differentiable operation, and thus we can't calculate the gradient. So in a related topic, other work has suggested a soft error metrics. So for example, by softening the F1 score or area under curve loss, you can come up with a differentiable version of the score metric, and then you can do this computation. So by softening, it means these hard decisions are kind of softened so that you have a function you can actually take a derivative of, and then you can compute this gradient. However, the tandem decision cost function we have here does not have such a soft version. So instead, we looked into the reinforcement learning. So in reinforcement learning, there is this kind of a simplified setup is like this. So the computer agent sees a image, or it's provided with some information from the game or the environment. The agent chooses an action A, and the action is then executed on the environment. And depending if the outcome of that action is good or not, the agent receives some reward. And in reinforcement learning, the goal of this, the whole setup, is to get as much reward as possible. So modify the agent so that you get as much reward as possible. And one way to do this is kind of with the gradient way. So we could take the gradient of the expected reward, so the reward averaged over all different setups and situations, and take a gradient of that with respect to the policy, with respect to the agent. So if we can do this, we can then, of course, update the agent to towards the direction that increases the amount of reward. However, we here also have the sad problem that you can't really differentiate this hard decision part, where we choose one specific action of many and execute that on the environment. So we can't differentiate that, and we can't compute the gradient. However, there is a thing called policy gradient, which kind of estimates this gradient with this kind of equation, where instead of calculating the gradient of the reward directly, it computes the gradient of the log probabilities of the selected actions and weights them by the reward we got. And this has been shown in reinforcement learning to be quite effective strategy, and also been shown that you can replace the error, the reward, with any function, and then by running this, you will also get the correct gradient, so you can get the correct same results with enough samples. So going back to our tandem optimization, where we had the same problem of hard decisions which we can't differentiate, we just apply this policy gradient here, the policy gradient theorem here, where the equation is more or less the same, just with different meaning. So we then proceeded to test this, how well it works, with a rather trivial setup. So we have two datasets. We have the FoxLab1 dataset, and more specifically the speaker verification part of it, and then we have the ASV spoof 19 for the synthesized speech and the other countermeasure tests and labels. And for ASV task, we extract the X vectors using the pre-trained CalD models, and for the ASV spoof, we extract the CQCC features. And these are fixed, so these are not being trained in this setup. We then train the ASV system and the CM system as normally done using these two datasets, and then evaluate them together using the TDCF cost function as presented in the ASV Spoof 19 competition. After this, we take the two pre-trained systems and perform tandem optimization on them as previously shown, and then finally we evaluate the results and compare them with the pre-trained results and see if it actually helps. So, less surprisingly, the tandem optimization helps in a very short nutshell. So, one way we see this is by looking at this learning curve, where on the x-axis you have the number of updates you do, so you can compare to these curves where you have the loss and the number of epochs, and on the y-axis you will have the relative change in evaluation set compared to the pre-trained system. So if it was 0%, it means the metric did not change since the pre-trained system. So the main metric we wanted to minimize is the minimum the decision cost function normalized, and this indeed decreased over time as we did this tandem optimization. So from 0% change it went to minus 25% change, so yes, it improved. Then we also studied how the individual systems changed over the training. So for example, the countermeasure equal error rate in the countermeasure's own task, just detecting if it's spoof or not, it also improved by around 10% in this task. But interestingly, the ASV ER increased over time, and we hypothesize that because when we evaluated the ASV system in countermeasure task and the countermeasure in the ASV task, so flipped tasks, we noticed that after this tandem optimization, they have improved in their each other's tasks. So ASV was better in countermeasure tasks, and countermeasure was also slightly better in the speaker verification task. So we hypothesized that this kind of outweighed the speaker verification system's normal task of detecting correct speaker, and it started to kind of detect the countermeasures, the spoofed samples instead. So we also compared this to a simple baseline, where instead of using this tandem optimization, we just independently continued training the two systems using the same samples as in the policy grading method. So basically we just use the same samples and use the ASV samples to continue updating the ASV system, and then we use the countermeasure samples to update the countermeasure system independently, completely different from each other. And we see the same ASV behavior here, but countermeasure systems, the equal error rate just exploded in the beginning and then slowly creeps back down, and in the end, average over multiple runs, we see that the policy grading method improves the results by 26%, and the fine-tuning improves the result by 7.8%. But do note that the results on the fine-tuning have a lot higher variance than in the policy gradient version. But these all results are very positive, but this was a very initial investigation, and I highly recommend that you check out the paper for more results and figures. And that's all. So thank you for listening. Be sure to check out the paper and the code behind that link.